Just because atoms are going to be sharing electrons, or even if they're then transferring electrons in ionic compounds, that doesn't always mean that the scenario is perfect, that the two atoms are, in essence, getting along, so to speak. That just because they might share electrons to make covalent molecules, that the two atoms are sharing equally. It'd be like, say, there's only one piece of chocolate cake left, and do you cut the slice exactly in the middle so that each person gets it an equal half, or somebody kind of shave it a little bit to their side and they get just a slightly larger piece, yet they're still sharing the cake, right? I mean, still, each person got a little piece. So what we have are what's called bond polarity and molecular polarity. In other words, you analyze what is something called the polarity of an individual bond between two atoms. It doesn't matter how big the molecule is, you're just looking at two individual atoms and the bond that they make with one another. Or you look at the entire molecule, and that's going to be called molecular polarity. We'll talk about that after we finish with Chapter 7, talking about what the three-dimensional structure of the molecules are. But here in Chapter 6, we can go ahead and talk about what's called the bond polarity. And it's real simple in terms of evaluating, because you just look up the electronegativities on a chart for each of the two atoms that are making a bond with one another, and then see how far apart they are in terms of their electronegativity. Remember, the electronegativity is a measure of the attraction of that atom's electrons, but not just his own, the electrons of then the neighboring atom, or the one that he's trying to make a bond with. So you'll see on the little summary sheet here that there's a range of values for when you do the subtraction between the two atoms, that if they fall within a certain range, and roughly kind of works out to be that your lines of demarcation are, look to see if the difference is about 0.5 or if it's greater than about 2. If the difference in electronegativity is less than about 0.5, well, then what you're really saying is that neither of the atoms is really that much more attracting of electrons or stronger than the other atom. And so it's sort of like an even-steven tug of war between sharing those electrons. If you have an electronegativity difference between the two atoms that is greater than 2, now you're saying that the difference in electronegativities between the two atoms is so far apart, it means that one of those atoms is very much stronger in attracting electrons than the other, so strong in fact that he'll actually take the electron from the other atom. And the other guy with a low electronegativity, then he has such a low one that he doesn't or isn't able to attract the electrons, and so he willingly then will give that electron up. Well, see, what you've got then is that if you have a difference in electronegativity greater than 2 between the two atoms, you have the formation of a cation and an anion, because the element that had the stronger electronegativity is so strong that he actually takes the electron, and so then you'll have the formation of an anion by the other element then losing the electron. He becomes a cation. This is that setup of a metal and a nonmetal, or in other words, an ionic bond. So different literature values will give differences. I've got here difference of greater than 1.9. If you just roughly remember that it's about 2, some papers have said, only a difference of 1.7. I've seen 1.8. It's just roughly in the ballpark of about 2. Okay, that's going to be called an ionic bond, which then you're saying, yeah, you indeed did have an element that was so strong that it actually took the electron. In other words, you'll have that transfer. If you have covalent, then notice how that there's 2 different types of covalence. Now we have not just 2 types of compounds, we're going to have more specificity. It's not just ionic or covalent, but if you're covalent, are you polar covalent or are you non-polar covalent? Non-polar covalent, as you see, that's going to be designating that you've got that scenario where, the difference is less than 0.5, so those atoms are pretty much equally sharing. Think of it like that. Think of that as meaning that those atoms are doing their very best, that they will be equally sharing the electrons between them. And it doesn't matter if it's a single bond or a double bond or a triple bond. If their electronegativities are that close, it means that neither of the nuclei are pulling or tugging on those electrons any more than the other. Where the chemistry gets interesting is in the middle, where you have the difference between 0.5 and 2-ish. where you have two elements then that have sufficiently close enough electronegativities that one of them is not going to be able to take the electron away from the other, but yet one of them is stronger. I was liking it to having like a tug of war between Arnold Schwarzenegger and me. And so obviously I'm the stronger one, haha. And so, you still have both persons hanging onto the rope, aka valence electrons, so they're still sharing. There's some kind of a connection or a bond there. But it could be that then, indeed, one of those atoms is going to be stronger than the other. Well, so now we have a handout that from chapter 4, actually, and then I gave you another copy of it in chapter 6 on D2L that has some little cartoons that kind of describe this. So let me pull that up here in just a second. Okay, so you see this little picture here. This is a handout that you had in chapter 4 and in chapter 6, and it has the literal electronegativities that are on our scale. So here's your low, guys, and then remember that they increase as you go over and as you go up. So there's fluorine, he's the top dog, with an electronegativity of 4.0, meaning that they have the ability to attract electrons more towards themselves. So down here at the bottom then, these little cartoons, and it may be hard to read the little typing, but the little cartoons down here then are going to signify how that I've got a tug of war happening between two atoms that, like I've got here, the tug of war might be happening between, say, a chlorine and a sodium, where the rope that they're using in the tug of war is like the valence electrons. And so you have one element or one atom that is so much stronger than the other, and the other one then is weaker, and so then he's losing hold of those electrons. So in other words, he's losing his electron and he'll become a cation, and then the chlorine, he'll be gaining his electrons. He's going to become then an anion. And then you've got the formation of the ionic bond. There would be the difference then in electronegativities being greater than 2, because you'll see then how that chlorine has an electronegativity of 3, and then over here on the left you got sodium with an electronegativity of 0.9. Haha! So if you have an electronegativity of 3 minus 0.9, that's a difference of 2.1, you can actually quantify your ability to call that an ionic bond. Now for us, remember, we just look at it as being metal and non-metal. Well, yeah, go figure. You look at these electronegativities, and any of the guys that you have electronegativities for the metals that are to the left of the stair steps, and then you choose an element to the right of the stair steps, you choose any element from the far left of the table and then an element from the far right, metal and non-metal, their electronegativities are going to probably be greater than 2. And so we typically would just then call those guys ionic bonds. So you don't really have to have the numbers in front of you, because just physically on the periodic table, pick elements that are far enough apart, they're going to be then quantitatively come out to a difference of greater than 2. So probably not that big of a deal of having to know the numbers, okay? Likewise, you'll have a fair fight, so to speak, a difference in electronegativity, where say you're going to do a molecule of N2. Remember we drew his Lewis structure in the previous video? So of course, the same element, they'll have the same electronegativity. You can't get any more nonpolar covalent than that. In other words, on the scale of saying to what degree is one atom attracting the electrons more than the other atom in their bond, not a chance. You got a nitrogen making another covalent bond to another nitrogen. Here's our Lewis structure. This guy is pulling with the same intensity or the same strength of attraction that that nitrogen on the other side is. So all 6 electrons then are being shared equally between them because they have a difference of 0. So that's then a non-polar covalent bond. Okay, where the interesting thing's going to happen then, again, like I was saying, is what happens in the middle. So say like a molecule of HCl. You look up his electronegativity, 2.1. Chlorine's electronegativity 3.0, you get a difference of electronegativity in that mid-range, that in-between range. The behavior of that molecule then is called polar covalent, sort of like saying that something is polarized, okay? Let me start another page here. I'll come back. Okay, if you have something which is polarized, let me pull that tug of war page back here again. You have something which is polarized. It kind of reminds you of having the North Pole or the South Pole, or like having magnets, okay? That's going to be like this scenario that is in the middle, these guys here, okay? You've got both of them hanging on to the rope, aka they're sharing valence electrons with one another, but one of them is like barely hanging on, or he's trying to hold on. He does have sufficient strength to hold on, so he's got, no slouch at an electronegativity, but that it indeed does look like that there's another element that is a little bit stronger. In the cartoon here, it's kind of backwards. The H is on the right, and then my little Cl guy would be over here. Those guys sharing those electrons, let me go ahead and draw the entire Lewis structure in. Those guys sharing those electrons, it's as if then the chlorine, because he has a greater electronegativity, put a little hash mark across the arrow there, that's how we do it, is saying that he has then a greater pull, a greater electronegativity. Well, yeah, because he's farther to the right and up on the periodic table. Now, what that does then is that those electrons then, the two electrons being used as the covalent bond, they are not being equally shared. They are being unequally or unevenly shared. Meaning that the electrons that are being shared, they're actually going to be hanging out, probability-wise, more in the orbitals of the chlorine and away from where the hydrogen is. What this is going to do then is it's going to impart a slight, and the symbol for that, it looks like I'm trying to draw the number 8. It's the small case letter delta. Okay, you can practice. It's like you're going to draw the number 8, but you just stop before you finish off the last little loop. Okay, that's the Greek letter delta. By those electrons being pulled more towards the chlorine, it's going to impart what's called a partial charge. Okay, or you could think of it as being a slight charge. Okay, it's not a complete negative charge because the chlorine is not strong enough to take the electron away. Remember, that's what it is for ionic, when somebody can actually take the electron away and then become negatively charged and the other guy becomes positive. He's not taking the electron away, it's just that it's going to be hanging out more towards his nucleus than the hydrogen. Well, if he's going to become then slightly negatively charged, because the probability then of an extra electron hanging out more on his side of the bond, so to speak, that's going to then impart a partial positive charge then to the hydrogen. Now see what we've got here then are 3 different scenarios. You have a type of a molecule where you actually do, by golly, have a cation and an anion. That's the strongest of them all, that connection between a positive and a negative ion, because somebody really indeed was so electronegative that they could take the electron away from the other atom. You've got the scenario then where you have just simply no charge, nothing going on, even sharing. That's the non-polar covalent type of a bond. And then you've got this middle ground then where you're going to have the guy that is only slightly charged, but yet there is going to be then the ability for that molecule to exert either repulsion or attraction, because there is sort of this gradient of difference in charge, that there's more electrons hanging out on one side of the molecule than the other. So there's a distortion in the probability of where the electrons are found. They called, the fancy word for that is called electrostatic potential. And there are experiments that actually measure this. It's called a dipole moment. I'm going to write that down for you, because that's another important vocabulary word. Dipole. See the word pole, like a polar, like the North and South Pole, or like magnets. It's kind of the same thing. You have a slight positive, slight negative charge, and then it's called a moment, dipole moment. Okay, it's an actual experiment that they can measure just how strong is that attraction of having a negative and positive, slight negative and slight positive ends to those molecules. Okay, what we'll be seeing later on is when we look at the polarity of an entire molecule. Here we're just looking at 2 elements one at a time. But once we look at molecular polarity, we'll see that that is going to be responsible for a lot of the behavior then, and properties is what I'm trying to say, not not behavior, but properties of then molecules and substances, in order to motivate them to do chemical reactions. So again, that's kind of where we're headed, is to try to figure out how these guys are all interacting with one another. Okay, so let's do an example. Let me do another fresh page here. Okay, so let's say, for example, what if I had a more complicated molecule? Like, what if I did methane? Okay, that's natural gas. Probably you guys are running that at your house trying to stay warm. Okay, remember what I said is it doesn't matter how big the molecule is. When you're looking at bond polarity, you're just analyzing what is going on in one bond at a time. So like in this molecule, I'm going to quickly scratch the Lewis structure down. You go through and confirm that you could figure this Lewis structure out. Carbon is in the middle. It's going to be a symmetry thing. So carbon's the middle, the central atom, and then you've got the 4 hydrogens. Okay, so there's my Lewis structure. That what I would do then is I would look at just the polarity of that bond, the one between the carbon and a hydrogen. Now, I chose this molecule because once I figured that out, well, then it's the same for the other 3, okay? You don't do it all 4 angles or 4 bonds. You just do it for the one that's being specified. So I would look up the electronegativity for carbon. When you look on that sheet, you don't memorize these numbers. Again, these are always provided to you, okay? So I look up carbon, he's 2.5, and I got hydrogen, he's 2.1. Okay, so the difference then in electronegativity between these guys is 0.4. What that means is that that is essentially a non-polar covalent bond, meaning that that bond between that carbon and hydrogen, those 2 electrons then are essentially being shared evenly. Now, let me kind of mix it up a little bit, and let's have it be a little bit different. Let's have it be this time a molecule of chloroform. That's CH3 or CHCl3. Get my 3 to work there. CHCl3. Okay. So again, do my little arrangement. You guys can work out the Lewis structure on your own later. Confirm that you could come up with something like this all on your own. So you have carbon in the middle. See how you get carbon, hydrogen, chlorine. You got to decide who's the middle one. It's going to be carbon. Symmetry is not going to help you too much because you got 3 different atom types, chlorine, carbon, hydrogen. But step number 2, or rule number 2, when deciding the central atom on your sheet there from the handout from chapter 6, carbon needs to share the most. Carbon needs to share 4. Hydrogen only needs to share 1. And so does chlorine. Okay? So now I'll get my Lewis, or get my little valence electrons in for all the chlorines. Each of those chlorines had 7 valence electrons, so they're going to have 3 lone pairs on each of them. Okay. All right, so there's my Lewis structure. Okay, well, so see how on this one I actually need to do 2 analyses because I've got a carbon-hydrogen bond and then I've got a bond between a carbon and a chlorine. And then the other 2 are identical once I do the calculation between the C and the Cl. Okay, so look up carbon. All right, he's 2.5, chlorine 3.0. That's a difference of 0.5. So that's kind of borderline, right? That's kind of borderline, okay? If it's going to be about 0.5 or so, typically we'd probably go ahead and just say that that's going to be polar. Anything less than 0.5, then you're saying, they're going to be pretty equal sharing, okay? Well, so what that's going to mean then is that for that bond, just the bond between the carbons and the chlorines, I'll then have a slight positive charge on the carbon, and I'll have a slight negative charge then on my chlorine. And then it would be the same for the other 2 carbon-chlorine bonds as well. Okay, that sets up that bond then to be a polar covalent bond. And that's going to have implications to the properties of those molecules, okay? The carbon-hydrogen bond, we just did that one before, and we've already figured out that that one is nonpolar. So see, you can have all kinds of combinations. You can have polars and nonpolars all within the same type of a bond then, okay? The most complicated scenario, not really complicated, but the next scenario that you might have is, what if you had one of those polyatomic ions that you guys will be learning about, okay? So for example, what if I had nitric acid? If I had nitric acid, so I had HNO3, okay? Again, I'm going to scratch out the Lewis structure real quickly. You all would need to be able to do this then. Make sure that you could figure out how to do this yourself, okay? All right, so here's going to be the Lewis structure. Okay, so you just go through those steps. on the sheet, just that little checklist, how we did before, okay, and this would be my Lewis structure. So then you would have a nitrogen-oxygen bond, and now see, whatever result you get for that one, it'll be the same for the other two, because they're exactly the same kind of a bond. Doesn't matter whether it's single or double or triple. And then you'd have a hydrogen and an oxygen to do, okay? Well, oxygen, he's 3.5. Nitrogen's 3.0, so that's that 0.5. He's kind of right on the border, and yet there probably is going to be then a slight polarity to that bond. So all of those between the nitrogens and the oxygens, those guys are going to all be slightly negative, partial negative on the oxygen and partial positive on the nitrogen, okay? Whoever is the more electronegative element, that's who's the stronger one, so he's the guy that gets the partial negative, okay? And then down here you'd have hydrogen, he's 2.1, oxygen again is 3.5. Ha, you really got it going there, right? You got 1.4 difference between those guys, right? Okay, so definitely a polarity there. So you have a partial positive charge on the hydrogen and a partial negative charge on the oxygen. Last but not least, what if I had something like sodium nitrate? Here's a scenario where you have actually both ionic and covalent bonding taking place, because you would have the NO3 take that guy out. Okay. All right, so here's my NO3 structure. Okay. Oop, got another electron in there. But remember how that this guy, NO3, we did this, he has resonance structures, that he's a negative charge, and then you'd have your sodium, which is a positive charge. What the heck? Well, it's because literally one of those electrons, I'll do him in red, and then I'll keep the oxygen ones being blue. That electron from the sodium was being given to the NO3. You could make your ionic bond between this oxygen, or you could come and make him over here, or you could make him here, okay? But what's interesting then is that you're going to have a scenario where you'll have these guys being ionic, and then the rest of the bonds being covalent. You have both taking place. By just looking at the formula, you could tell that, though, because as soon as you see you have a metal, you know you have ionic. And then when you see that the polyatomic anion is all between nonmetals, nitrogen and oxygen are both nonmetals, then any kind of a bond which is a nonmetal and a nonmetal, that's covalent, okay? You can do the electronegativity just between these two guys and still be able to tell, because you've got sodium coming in at 0.9, and then you've got oxygen coming in at 3.5, okay? So definitely a difference of, what is that, 2.6, okay? So definitely you'll have a ionic bond between those two things, okay? So you can actually have then the polarity between the atoms be all of ionic and covalent. So for these guys, you have both polar covalent and you'd have ionic. We already did the subtraction between nitrogen and oxygen. So you have polar covalent and you have ionic all within one molecule.